Okay, so I would like to thank the organizer for this invitation. And in the talk, I will try to explain how one can extend all the results on the differential transcendence of the gamma function to any formal power series solution of a linear difference equation over the projective line. So let me start with a hierarchy of function. I will start by considering the ring of polynomial with integer coefficients, and then I want to form a fraction with this ring, and I will use the ring of rational fraction with rational coefficients. But if I want to find functions that satisfy polynomial equation, I have to switch to another field, which is the field of algebraic function, which has been introduced by Aline in his talk. And square of x is an example of an algebraic function because, well, square of x squared is x, okay? But usually when you want to do some analysis, when you end up by thinking that this field of algebraic function is a little bit too small to find a special function of interest, and then you're forced to jump to a very large field, which will be the field of Puiseux series with complex coefficients. So this hierarchy mimics a little bit the hierarchy for numbers, where you have the integer, the field of rational number, and its algebraic closure, and then all of a sudden you need to jump to the field of complex number. So you would like to find an intermediate field where you can grab a little bit more your function and handle the algebraic complexity. So here as a proposition, I will introduce this field dA, which is the subfield of Puiseux series that satisfies algebraic differential equation. By this, I mean that f and some of its derivatives satisfy a non-trivial polynomial equation with coefficients in the field of rational fraction. Okay, and so as examples, we have the exponential function, which satisfies a linear differential equation, as well as, for instance, the Weierstrass P function, which satisfies a well-known differential equation given by the equation of the corresponding elliptic curve. Okay, so now why are we interested in characterizing differentially algebraic function? Well, the first thing is that any rational function over an algebraic curve defined over Q is in fact differentially algebraic over Q. So you have plenty of examples of differential algebraic function that comes from geometry. The second thing that there are many important functions in number theory that are not differentially algebraic. And for instance, Hölder proved that the gamma function is differentially transcendental. And if you look at the functional equation connecting zeta and gamma, then you end up by proving that zeta is itself differentially transcendental. Moreover, for certain class of functions, for instance, the Malor functions that I will introduce later on, you have some transfer properties between the algebraic relations satisfied by solutions of this kind of equations and the algebraic relations among their values. So for instance, if you are able to prove that such a function is differentially transcendental, then you will end up with the fact that the evaluation of such a function and its derivative of certain algebraic points are algebraically independent. Okay? And finally, and I will explain this in detail, the differential algebraicity of a formal power series measures the algebraic or asymptotic complexity of the sequence of its Taylor coefficients. So having a differential algebraic equation satisfied by your power series allows you to get more information on the sequence of its coefficients. Okay, so let me first start with the subclass of differentially algebraic function, the class introduced by Aline in his talk and by Stanley in the 80s. So I will repeat a little bit some of Aline's what Aline said. So you start with a formal power series and you say that it's definite over Q of X if it satisfies a linear differential equation over Q of X. Okay? And then you have many nice properties for the class of definite function. The first of them is that a definite function must have a finite number of singular points. And in fact, you can use the converse of this property if you find a function that has an infinite amount of singular points, then it's not definite. Okay? So you can a little bit decide whether a function is definite or not by just looking at its singularities. Another thing mentioned by Aline, if your formal power series satisfies a linear differential equation, well, its Taylor coefficients satisfy a linear recurrences with polynomial coefficients in N. So you get another information on the sequence of coefficients, and this allows you to find these nice asymptotics for the coefficients. Once again, if you want to prove that you have a given formal power series and it's not definite, you can try to prove that the asymptotic of the coefficients do not satisfy such a nice asymptotic. Okay, so if I cannot find evidences that my given formal power series is not definite, then I will try to prove that it is definite, and there are some methods. So one of these methods, which has been used a lot in the enumeration of this works confined in a quadrant, is to realize your formal power series as a diagonal of a definite function. Okay? So I have a definite formal power series, which I expand here. And the diagonal is just to end up with a one variable function where you have extracted the diagonal of this sequence of coefficients. So in enumerative combinatorics, people who are using the functional equation that Aline showed you sometimes to produce a rational function out of an orbit sum. And then the generating series people who are interested in was the positive part of this rational function. So the part of the expansion of the rational function where the variable had positive exponents. And taking the positive part of a formal power series, it corresponds to taking some diagonal. Then it was how they proved that generating functions for certain works were definite. So, for instance, here is a representation of this hypergeometric series as a diagonal of a rational fraction. Okay, and then what you can also do is try to guess a linear differential operator for F, and Aline explained some of the methods, and then you can try to certify this guess. Okay. But what happened to the class of differentially algebraic power series? Well, it happens that this class is much wilder. So the first thing, okay, you can have some asymptotics on the sequence of coefficients, but they are very large, and it's not very useful to try, given a formal power series, to try to deny such an asymptotics. It would be difficult. Okay? Another thing that is unfortunate is that a differentially algebraic power series might have an infinite number of singular points. So we have the same example. So I didn't copy Aline's slides. So the generating function of partition of integers. So where you want to count the numbers of ways of writing a given integer n as the sum of smaller integers. Well, it can be written as this Euler product, and you see that it has an infinite number of singularities. But this generating function is connected via a change of variable to modular forms, and it's therefore a differentially algebraic function. So in that case, you cannot count on the argument of the amount of singular points to say that a function will be differentially algebraic or not. Okay. And finally, the diagonal of a differentially algebraic power series is not necessarily differentially algebraic. So here is an example that I found in Lipschitz and Rubel paper. So you consider this theta function here and the exponential function, and both of them, they are differentially algebraic, but it happens that the diagonal of this product is this function, which is not differentially algebraic. So it's an argument on the gaps between exponents in your expansion. Okay. So let us come back to our favorite example, the gamma function. And in fact, Hölder proofs relies heavily on the fact that the gamma function satisfies a nice difference equation, which is as follows, where in fact we have a very simple dynamics on C of x, which is given by replacing x by x plus 1. Okay, so in this talk, I will try to show you how one can develop a Galois theory to determine the differentially algebraic relation satisfied by solutions of linear difference equation, and how you can use this Galois theory to characterize all the differentially algebraic special functions, solutions of difference equation over the projective line. So to say the field of coefficients is the field of rational fraction, or over elliptic curves, where my field of coefficients of the equation will be a field of elliptic function. Okay, so first I need to introduce some terminology, coming back from Kohn, of difference algebra. So difference field is just a tuple made by a field K and a field endomorphism sigma. The first example, which is the one suitable for gamma, is the field of rational fraction, where you consider the shift of the variable x by 1. The second example is you can consider for p a non-zero integer the morphism of the field of rational fraction here, which exponentiates the variable x by p. It is called the Malher operator. But you may notice that this morphism of the field of rational fraction is not surjective. And then to have a field, a difference field, we need to ramify the variable x and to look at the direct limit of this field, which are denoted by Cx x star. And then on that field, you can extend the action of the exponentiation by p, and you find a difference field. Okay, so now here is my elliptic example. I fix a complex lattice, lambda 0, and I am denoted by k lambda 0, the field of lambda 0, periodic meromorphic function. So these are the rational fraction of this elliptic curve. And now I choose a positive integer, And I can consider the morphism of k lambda 0 given by sending x onto its multiple by q. Okay? And once again, you see that it's not surjective, and you will have to do the same process as done for the Malor operator. You will have to look at all the elliptic function for the sublattices of the chosen lattices lambda 0, and then you end up by having a difference field. Oh, what do you mean? Oh, yeah, we can do smaller, but here also we could do smaller. We could just look at the ramification in powers of p. It's not such a big issue. We could look at smaller field. So one field of importance in this difference field, it's the field of difference constants, which I denoted by k sigma. It's just the element of my base fields are fixed by the difference operator. Okay, and in all the example above, this field of constants are the field of complex number. So, because perhaps most of you are more used to differential equation, a difference equation is just a discretization of a differential equation, and you can think at sigma minus identity as replacing the derivation. And here, the differential constants, these are the elements that are sent to 0 by the derivation. And here in that context, it will be the one fixed by the automorphism. Okay, it's this certain analogy. Okay, so now what is a difference system? I fix a difference field and an invertible matrix with coefficients in that field, and I can consider the following functional equation: sigma of y is equal to a of y. Okay, and in analogy with difference equation and difference system, if you start here with a differential equation, then you find a differential system by looking at the companion matrix. Well, here it's the same process. You have a difference equation, and then you can form the associated companion matrix, and you find a difference system. And under Mild assumption on the difference field K, you can prove that any difference system is equivalent, gauge equivalent, I will not be more precise, to the companion matrix of a difference equation. Okay, so let me give you an example coming from automata theory. So I will consider this formal power theory. Well, the AN are minus 1 b to the n, where Bn is the number of pairs of consecutive 1 in the binary representation of n. So this AN is what is called an automatic sequence because it can be generated by a finite automaton, where the input is just the binary expansion of n and the output is AN. Okay? So if you form the following column vector, you see that this column vector satisfies the following equation, where here the base field is this field of ramified rational fraction, and this is the 2 Malor operator. Okay? And I will say that any Laurent series with a complex coefficient solution of such a system is called the Malor function. Okay. So usually a Malor function, you will look at algebraic coefficient over Q to have transfer properties, but here I am a little bit changing the terminology. So now let me give you an example in the elliptic setting. You fix a complex lattice and Q a fixed integer, and you consider the Weierstrass zeta function. It is the antiderivatives of the opposite of the Weierstrass P function. And it happens that if you look at this squared matrix, it satisfies the following difference system, where the dynamic, is x goes to qx. Q is a fixed integer. Q is a fixed integer. Okay. So these coefficients, it depends on Q, of course, and on the zeta function. Okay, so you have a discrete equation for the Weierstrass zeta function. Okay. So I am interested in differential algebraic relation among solution of differential equation. So first, let us ask about the algebraic relation. So Michael last week gave a talk about the differential Galois theory. This Galois theory for linear differential equation. So I will be a little bit sketchy about the Galois theory of differential equation. I will try to just give the ideas. So you start with a difference field with a field of constants that is algebraic closed and a difference system. Okay. And then what does this difference Galois theory? Then it will code the algebraic relation satisfied by the entries of an invertible matrix U, solution of your system, as a defining equation of a certain Galois group, which is, I'm a little bit cheating, the automorphism of the field extension generated by the coefficients of U that commutes with sigma and that leaves K invariant. Okay? And you can represent this abstract group as a linear algebraic subgroup G of JLN of K sigma. So I just show you briefly how it works. Okay, I will assume that the constants of my field of solutions are the same than those of my base field. And I take an automorphism which commutes with sigma and leaves the base field invariant, okay? Then I let this thing act on my equation. So since it commutes with sigma, I have sigma of 2 of U, which is equal to the image of this product, but A is in the base field, so it is fixed. And here I have 2 of U. Okay? So this means that 2 of U is another solution of my initial system. And since I have this assumption, this must be a multiple of my formal series solution via some invertible matrix with coefficients, constant coefficients. Okay, so this gives me a representation of my abstract Galois group. Okay. And it's a linear algebraic group. It means that you can see its image in GLN as a set of matrices which satisfy certain polynomial relation. Okay? But you know there are three steps in classical Galois theory. You code the algebraic relation satisfied by roots of a polynomial in the equation of your Galois group. But this defining equation of your Galois group, they have an impact on the relations of the coefficients of your equation. So, in fact, via this dictionary of Galois correspondence, I can see the algebraic relation satisfied by the entries of, by the coefficients of a solution via some algebraic relations among the coefficients of my system. And this relation, this is something I can put my hand on. Okay. So now what does this parameterized Galois theory? So we need to find a derivation and a suitable one. So I start with a difference field of characteristic 0 and a derivation of k that commutes with sigma. And such a triplet of operator and a field, which will be called delta sigma fields. So first example, the one for gamma, the shift, and the usual derivation. For the Malor operator, it's a little bit more tricky. You need to add the logarithm to find that this derivation commutes with a Malor operator. And finally, in the elliptic setting, where you multiply x by an integer q, then you have this derivation. So what do I want? That my derivation commutes with sigma. It's just to let it act on the solution. So if I have a solution of a different system, I can derive it. And this commutes, so this is sigma of delta of u, and then I am using the Leibniz rule. Okay? And then I find a new different system satisfied by u and its derivatives, which is of the following form. And I can go on. Okay? So you could say, okay, why don't you compute the Galois group of this sequence? Well, the Galois groups, the matrices are going larger and larger, and you cannot compute an infinite amount of classical Galois group. So we will find a shortcut, okay, to compute all these classical Galois group in a row. Okay? This is the idea of this parameterized Galois theory. So we are fixing a field with an automorphism and a derivation. And the parameterized Galois theory we built with Michael does as follows. So you code the differential algebraic relation among the solutions here into the defining equation of a Galois group. So here I am cheating a lot, which you can see as the automorphism of this huge field extension where you have plugged the solution and all their derivatives that commutes with the derivation and with the difference operator. And then you can do almost the same process as before. You can represent it as a subgroup of the group of invertible matrices with constant coefficients. But this time, this group will be given by polynomial differentially algebraic relation. Okay? And so you say, okay, but if I have a constant matrix, this delta of C will be equal to 0. What is the meaning of that? So one can give a precise meaning to this. For instance, the first to have studied this object is Cauchin, and he looked at the points of such objects into differentially closed fields. There are some model theoretic way to handle these objects, but let me think just in terms of equations, not in terms of points. So if I am looking at the additive group, well, we know that there are not a lot of subgroups algebraic given by a polynomial equation here. Essentially, I have two, okay? But here I can find some subgroup, the one, for instance, given by the solution of this equation. Okay? Solution of this equation, we all know that solutions of linear differential equation, they form a vector space, so it's an additive group. And so if you want to look at their points, well, you will see that it's like that, okay? So this, well, if you want, you can think of this differential algebraic group just in terms of their defining equations. And then once again, the differential algebraic relation between the solution, that will be coded in some differential algebraic relation among the coefficients of your given system. Okay, so there are Tannakian approaches of this. It's just you can make the different system into different modules and then have a Tannakian category. And this action of deriving the system, it will give you an underfactor of this category, which is called a prolongation. Okay, and this prolongation, then you can define what is a differential Tannakian category with such an underfactor. Okay, but let me switch that. And there is also a version for algebraic equation, which goes back to the work of Malgrange and has been implemented by Anne Granier for Q-difference equation and generalized by Guy Casal. Okay, so let us start with simple equation. So rank 1 on non-homogeneous with some B in my base field. Then, in that case, it's not difficult to see that either U is differentially transcendental, which is equivalent to the fact that my parameterized Galois group is equal to GA. Okay? Or I will have a differentially algebraic solution and a proper subgroup. And as I told you, proper subgroups, they are defining equations, they are just linear differential equations with constant coefficients. So this result is due to Philly scarcity, but you can see it's just as also the fact that algebraic subgroup of vector groups, they are given by linear equation. Okay, so now so we are in the second case. What happens on the coefficients of our equation? So the fact that we are on this second case, well, you use parameterized Galois correspondence, and you must have such a relation on the coefficient B of your equation. So this linear differential equation applied to B, it gives you something of the form sigma of G minus G. So let us see what it gives on gamma. Okay, so it's easy to see that gamma will be differentially algebraic if and only if its logarithmic derivative is. So you compute the equation for the logarithmic derivative, and you see that it's of the above form, where B is equal to 1 over x. So we argue by contradiction. Suppose that gamma is not differentially transcendental. Then it is differentially algebraic, as well as its logarithmic derivative. We must have this relation on the coefficients. This gives that I can find some non-zero complex number, and G a rational fraction, so that this identity holds. Okay, but then it's easy to see that it cannot be the case. So if the CI are non-zero, then x equals 0 is a pole here. But and it is the only pole here, okay? But then it must be a pole there. Let's say it is a pole of G of x. 0 is a pole of G of x, but then -1 must be a pole of here. Otherwise, it's a pole there. And then you made these arguments. If it's -1, it's a pole there, and it must cancel there. And then I end up by saying that on this side, you must have a pole that is not 0. And you end up with a contradiction. Okay. So this proof, in fact, it's just a rephrasing of Hölder's proof. So Hölder's use elimination among polynomial differential algebraic equation, which is in fact hidden in this statement of classification of differential algebraic subgroup of the additive group. Okay, so let's go to something more difficult. So I start with the difference equation, and I will assume that I can compute its difference Galois group without the derivation. And this Galois group, which is an algebraic group, is a simple algebraic group. Then one can prove that either the solutions of this system, they are all differentially transcendental, and then my parameterized Galois group is coincide with this algebraic group, or the parameterized Galois group has a very simple form. It is given by the equation delta of C equals 0. So this is a deep result. This relies on the deep result of Phyllis Cassidy. And if you are using the parameterized Galois correspondence with this, then you will find that you must have a matrix with coefficients in your base field so that this equation holds. Okay? Well, it's a little bit tricky. We can rephrase it in another way, in the sense that the difference system here will be compatible with this differential system there. Okay, and by compatible, I mean that you can find a full basis of solutions of these two systems in somewhere. Okay. And perhaps some of you have noticed, but the Frobenius structure, in a certain sense of a differential module, it's an instance of this compatibility. Okay? So to say, if you start with a different system and with a Galois group that is simple, then either your solutions are differentially transcendental, or in a certain way, they will satisfy a linear differential equation. This is a model. So it's very powerful. It tells you the form of the differential algebraic solution that can satisfy your solution. Okay. So as I said, it relies on the classification of Cassidy of Zariski-Dense differential algebraic subgroup of simple group. There is also proof of the statement by Kiso, where I use the language of foliations. Okay, let me switch back to the case of Malor equation. So we have Malor difference system, where the Malor operator is the exponentiation by P, and my base field, you have just ramified the variable X. And what we proved with Boris Adamczewski and Thomas Dreyfus is the following dichotomy. You take a Malor function, then it is either a rational fraction or it is differentially transcendental. You really have a dichotomy. It's a very simple object or it's a very wide object. Okay? And the corollary of these results is that you pick up a Malor function, it will be algebraically independent from any differentially algebraic Puiseux series. So you get a result of algebraic independence out of this statement. Okay? And in fact, we prove this dichotomy, rational versus differentially transcendental, for any Laurent series solution of Q difference equation over C of X. And also for shift equation, well, we have, we had an assumption because we don't want to say something stupid. You see the exponential. It satisfies the equation sigma of y is equal to E y, but it also satisfies y prime is equal to y. Okay, so when we prove this theorem, we have this assumption that the solutions here, they are not only Laurent series solutions, but they are not of exponential type, which was technical argument. And then Thomas refined this result and prove that if you take any formal Laurent series solution of a shift equation, that is differentially algebraic over C of X, then it belongs to a certain ring generated by exponential function. But here you have some field of L periodic function, so L is an integer, and an L periodic function might be differentially transcendental. So this result, it's just belong to it, not an equality. One has to take care about that. This is a difficulty when you have constants. L periodic functions, there are some sort of constants, which really might have any kind of behavior. Okay, so my idea is to show you how one can prove that just by articulating these classification results for differential algebraic group I gave you with some non-results, for instance, for the Malor equation. So Malor in the 30s proves that any Malor function is either rational or transcendental. This was the first dichotomy. Okay, then Bézivin proved the same dichotomy. Either a Malor function is rational or it cannot be definite. It cannot satisfy a linear differential equation. So this theorem by Bézivin can be rephrased, and it has been reproved by Reinhard Schäfke and Michael, by saying that a Malor system that is compatible with a differential system, it must descend to the field of complex number. That is, you can find a gauge transform of this equation so that it becomes an equation with constant coefficients. So Reinhard and Michael have done this for any difference operator on the projective line and prove a similar result. It's a hard machinery to prove that. And as a corollary, you can find a constraint on Malor systems that are compatible with differential systems. They must have an abelian Galois group. So, each time your Malor system has a basis of solution who satisfy linear differential equation, then the Galois group must be abelian. It's a very strong constraint. Okay? And finally, there is a result on the differential transcendence of such kind of an equation, which is the rank 1 case of our theorem, non-homogeneous. So Randé and Nguyen proved by different means that solution of such kind of equation, it's either rational or differentially transcendental. Okay? So now I want just to show you how we prove the results. Well, we do it by an induction on the rank of the system. Okay? For a system of rank 1, it is Randé or Nguyen's result. It's either the solution are either rational or differentially transcendental. Okay, so let's move to the rank n. So I can assume that there are two cases. Either the classical Galois group of this equation is non-solvable. Then it must have a simple quotient, and we can reduce to the case that, well, this equation, it has a simple Galois group as classical Galois group. And then I am using this classification. I know that when my different system has a simple Galois group, then either my solutions are differentially transcendental or my system is compatible with a differential system, a linear one. So let us assume that we are in that case. So the Galois group of this guy, it's a simple algebraic group, but this system is compatible with a differential equation. Well, we use Schäfke-Singer and RH-Singer results. Compatible systems, they have a abelian Galois group. It's done, we have a contradiction. Okay, and then we are reduced to the case where the Galois group is solvable, and then you can use your induction hypothesis to reduce your statement to study the or theorem on such kind of system. And here it's once again the results by Randé and Nguyen. So our proof is just a dévissage of the Galois group, and at each step we use essentially the results on the rank 1 equation and these results on the compatibility of different systems with differential 1. Okay? So we used the same strategy for Q-difference system above elliptic curve with Ehud de Chalit and Julien Roch. So we proved the rank 1 assumption. Any differentially algebraic Lorentz series is of solution of such an equation. It's of the form XRG with G in here. Okay. We have also a classification of compatible system in that elliptic cases. And in our case, the system does not descend to the complex number. But we can show that any fundamental solution of such a compatible system has a fundamental matrix of solution in that polynomial ring where you have the variable x and you had the Weierstrass function. And finally, when we start with a compatible system, then we prove that the Galois group is solvable, the classical one. And this ends up by proving that any Lorentz series solution of a linear equation of this type over K is differentially algebraic over K if and only if it belongs to this polynomial ring. So you have any differentially algebraic solution by just adding x, 1 over x, and the zeta function. Okay, so let me conclude this talk. So more generally, our results fits in the following setting. You have a functional equation in one operator, theta 1, over some field k, and you have functional equations with respect to another operator, theta 2. Okay, and you are wondering, can you find some condition on the operator so that, for instance, solution sets are small, the common solution set. So, for instance, the solution of this kind of equation, which is also a solution of this kind of equation, belong to the base field. Or you might ask a more difficult question, are solutions here algebraically independent there? Okay. So there are many questions. So with Boris, Adamczewski, Thomas Dreyfus, and Michael Wimmer, we solve this question here for difference operator, two Mahler operator, but linear one in that case. Okay. So, for instance, for linear difference equations, there is only for us one remaining case, which is the most important and difficult, because if you want to look at automorphism over algebraic curve, there are only two cases where the automorphism is of infinite order, the projective line and the elliptic curve. And so we are trying to have similar results when you are looking at translation map over elliptic curve. And we already have rank 1 and compatibility results, but there is some issue, technical issue. Okay, and well, if you ask what are the non-results for algebraic difference equation over the projective line, there are some results. For instance, this Ritz theorem. So Ritz characterized any differentially algebraic solution of this kind of difference equation where R is a rational fraction. So there are cosinus, Weierstrass elliptic function. And in fact, if you look at solution at the inverse of such a solution, then you end up by wondering, by studying, in fact, what is called the renormalization of the dynamic. So here the dynamic on P1, it's this rational fraction. And you are wondering if this f minus 1, f is the solution of this equation, is differentially algebraic or not. And here, well, the dynamic R, it has, there are some conditions of R, it has one fixed point, and it's an attractive fixed point. So in fact, when this renormalization of the dynamics are differentially algebraic, it means that you can cover your dynamic with some abelian dynamic. So for instance, the translation over an elliptic curve or an exponentiation of x. Okay, so what I mean by this remark is that each time there are some abelian groups coming into the pictures. So this makes a hope that, yeah, well, there is a hope to classify this kind of solution because each time there is a geometric reason for the solution to be differentially algebraic. And so I will end here. Thank you for your attention.